Okay friends, in the last video we have learned how you deal with a constraint motion and come up with the equation related to that. Now we are going to take a few questions and we'll try to apply whatever we have learned just now, right? So we have listed 6 questions. Let us take one by one and understand how we will find out the equation related to constraint. When I say equation related to constraint, I do not mean that you should write force equal to mass times acceleration equation. What I mean is, you will see multiple blocks here, right? So you will assume acceleration A1 of 1 and A2 and A3 for the other blocks respectively. We need to find out relation between the acceleration. Okay, that's all we want to do right now. Fine. Now you may want to try these 6 questions on your own. So for that you need to pause the video and you can try your own, and then you can see how and what all you can learn if you have gone wrong wherever you have. So let us see the first question. In this question, what do you think is the relation between A1, A2 and A3? Now when M1 pulls M2, if M1 moves by X, M2 will also move by X, right? Because the string is connected between them and it is inextensible. So acceleration of A1 must be equal to acceleration of A2, right? And where the string X goes, it goes in the motion of M3 down, right? So acceleration of A3 is also equal to A1 or A2. So the constant relation for this particular question is A1 equals to A2 equals to A3. Fine. Now let us see the second question. In the second question, we have 3 masses. This particular pulley, first pulley is fixed, whereas the second one can move, right? So let us try to understand how to deal with this situation. Now this particular situation can be dealt in 2 ways. One way is to visualize the relative motion, and in second way we can find out using the work done by the tension force and equate that to be 0. So let us try both the method. First way, we will try to solve this using relative velocity visualization. Okay? So I'll make some room to write. Fine. So if this M1 goes with acceleration A1 upwards, okay, this pulley will also go down with A1, isn't it? Because the string is inextensible. So whatever distance this moves, M1, same distance pulley will go down. Fine. So this is in terms of displacement. Now when you take a derivative of displacement, you get velocity and acceleration. So if their displacement are equal, their acceleration must be also equal. Now, if you can visualize, M2 will move because M3 is moving and pulley is moving because of these 2 motion, right? But with respect to pulley, with respect to this pulley, acceleration of M2 will be equal to acceleration of M3, isn't it? With respect to pulley, whatever distance this moves, same distance this must also move, because even the second string is inextensible. Fine. So if relative acceleration, I assume for A2 is, for M2 is A2, and for M3 it will be automatically down A2. Now this A2 is relative acceleration with respect to pulley. Its total acceleration will be relative acceleration plus acceleration of pulley. Fine. So A2 is up and A1 is down. So net upward acceleration for M2 is A2 minus A1, right? And net downward acceleration for M3 is A2 plus A1, right? So acceleration of M1, if it is A1, then acceleration of M2 is A2 minus A1. This is acceleration of M2, and acceleration of M3 is A2 plus A1. This is acceleration of M3. Fine. So we have got a relation between the acceleration of 3 masses. And if you can see, here acceleration of m2 plus acceleration of m3 is 2 times the acceleration of m1. Right? Now let us see how we can solve this constraint equation, or how we can get this constraint equation using the work done by tension force. Okay? So if suppose m1 moves up by x1 and m2 goes down by x2 and m3 goes down by x3, then work done by T1 is how much? T1 is the force, displacement is along the direction of force, which is x1. So work done by T1 is T1 x1, right? And work done by T2 on M2 is how much? T2 on M2 is upward and displacement is down, which is x2. So this is minus of T2 x2, right? And work done by T2 on M1 is minus of T2 into, on M3 is T2 into x3. I have assumed that both M2 and M3 are going down by x2 and x3 distance respectively. You can also assume that they are going up by x2 or x3, or one is moving up and other is going down. So that won't change your final answer. Okay? Right now I have assumed that both are going down by x2 and x3 respectively. So total work done by tension must be equal to 0 because it is internal force, right? So what I'll get total work done as T1 x1 minus T2 x2 minus T2 x3 is equal to 0, right? And if you see the free body diagram of this pulley, which is movable, you'll find out that T1 is equal to 2 times of T2. If you draw free body diagram of pulley P2, you'll get T1 force here, and this is T2, and this is T2. You'll get T1 minus 2T2 is equal to mass of pulley into acceleration of pulley. Mass of pulley is 0. So T1 minus 2T2 will be equal to 0. So T1 is equal to 2T2. So if I substitute that, I'll get 2x1 minus x2 minus x3 is equal to 0. If I substitute T1 as 2T2, T2 will get cancelled, you'll get 2x1 minus x2 minus x3 is equal to 0. Right? And then if you take double derivative of this equation, you will get 2 times acceleration A1 minus A2 minus A3 is equal to 0, or A1 is equal to A2 plus A3 by 2, right? Similar thing we got earlier also. So you can solve that particular constraint equation, or you can get that equation by using 2 methods, right? Now look at the third question. In third question, there is a hinge which connects the string from here to the movable object M2, and this pulley is also movable, whereas this pulley is fixed. Fine. I need to find out relation between this acceleration and acceleration of M2. Fine. So work done by tension should be 0. So T1 into movement of M1, let us suppose x1. If it is up, it must be down, right? M2 should go down. Let us assume that M2 goes down by x2 and M1 goes up by x1. So total work done is T1 x1 minus T2 into x2, right? T2 is up, but displacement is down. So this total work done should be equal to 0, right? And again, if you see the free body diagram of this pulley, you'll get T1 is equal to 2 times T2, right? So if I substitute that, I'll get 2t2 x1 minus t2 into x2 is equal to 0, or x1 is equal to x2 by 2. And if I take derivative of displacement 2 times, I'll get a1 is equal to a2 by 2. So we have got relation between acceleration of m2 and acceleration of m1. Okay? Now look at the fourth question. In this question, we have one movable pulley, and the diagram is, I think, self-explanatory, right? We need to find out relation between acceleration of m1 and acceleration of m2 again. Now here also, let us try to use work done by tension should be equal to 0 in the entire system. So T1, let us assume that this goes up by x1 and this goes down by x2. So T1 into x1 minus T2 into x2 should be equal to 0, right? And if you see the free body diagram of this pulley, you will have, this is T1 force and T2 force. You will get T2 equals to 2 times of T1, right? So you will get T1 x1 minus 2 times of T1 x2 equals to 0. So x1 is equal to 2 times of x2, right? And if you differentiate this again 2 times, you will get acceleration of first object is equal to 2 times acceleration of second object. Okay? So see how easy it is to get the relation between the acceleration if you follow these standard procedures. Okay? Now let us try little bit more involved problems, question number 5 and question number 6. In question number 5, there is a bar which is supported horizontally and it can only move vertically. And because of its vertical motion, this wedge is moving on the right hand side. Okay? We need to find relation between the acceleration of this bar and acceleration of the wedge. Right? Here, you will see that the standard procedures may not be applied in a straightforward manner, and at times you have to use some sort of mathematics or common sense to arrive at the constraint equation. For example, in this question, here you have to visualize that this wedge has moved little bit. If this wedge has moved little bit, then this bar has to move this distance, this dotted vertical line distance, isn't it? Suppose this dotted line vertical distance is y and this distance is x. Right? So can I say x is the movement of the wedge and y is the movement of bar? Isn't it? I can say that. Now what is the relation between x and y? I'll see that this angle is alpha. Right? If this is alpha, then this is 90 degree, this is 90 minus alpha. And what about this angle? This angle will also be 90 minus alpha. These are alternate angles. So you will get tan of 90 minus alpha is equal to x by y. Right? So what I will get is x is equal to y cot alpha. Right? If I differentiate this twice, I will get acceleration of wedge, which is because of x, is equal to acceleration of bar, let us call it as a1 times cot alpha. Fine. So you have seen a problem where none of the standard procedures may help you. But still, if you apply the basics properly and come out with proper visualization, you will get the relation. Okay? Let us see question number 6 now. Fine. In this question, what is happening is that you have two fixed pulleys and the end of the string is tied with a hinge which is on the ground. And this block, when it comes down, because of its coming down motion, this wedge is moving forward. So can you visualize the motion of each mass? It is very easy to visualize m1's acceleration, right? m1 will move in horizontal direction. That is pretty straightforward, right? Whereas this m2 as it is moving down, it is also moving forward with the wedge, isn't it? So m2 has two acceleration. One is vertically down and other is horizontal direction. The horizontal acceleration of m2 is same as that of wedge because it is moving with the wedge in the horizontal direction. But vertical acceleration A2 need not be equal to A1. So what is the relation between A1 and A2? So let us try to solve this particular situation using work done by tension. Fine. So T is the force acting on M2. So if M2 goes down by a distance of x1, then work done by tension T on M2 will be T into x1, right? And if you look at the wedge, wedge is experiencing a horizontal force of T, right? So work done by this tension is equal to what? If suppose wedge moves by a distance of x2, then work done by this tension force is T times x2, right? Now work done by tension on M2 will be negative because I have considered M2 is going down and tension force is up. So it will be minus of this is equal to 0. Now you will get x1 is equal to x2. And if you differentiate it twice, you will get acceleration of first object is equal to acceleration of second object. Now this A2 is not a total acceleration on M2. A2 is only downward acceleration on M2. There will be horizontal acceleration on M2 also, which is A1. And A1 happens to be equal to A2. So whenever you draw a free body diagram of M2, you must show two acceleration. One is like this and other like that. And when you write net force is equal to mass times acceleration along horizontal direction, this acceleration will be featuring, and along vertical direction that acceleration will be featuring. So net acceleration of this mass will be root over A1 square plus A2 square. Fine. So this is how you solve these 6 problems. Let me give you one question as assignment. Try this your own and let me know whether you get the final answer on the comment section of this video. Okay, and we will discuss it later. So I'll just rub this and give you one question. Fine. So here is the question. We have mass m1 and m2 which can freely move. You need to find out what is the relation between acceleration of m1 and acceleration of m2. These two pulleys are fixed. Even this is fixed on m2. These two are fixed on the wall. Okay? This string wrapped around from m1 and it goes around and then it connects m2. Fine? So try this question and let me know in the comment section if you have any difficulty and we'll discuss it out. Right? So thanks for watching the video.